let's take a look at internal resistance, which is denoted by small r. The cells offer resistance to the flow of the charge through them, which means that some energy must therefore be used to move the charge through the cell. The energy lost per coulomb of charge through the cell is the lost volts, or V internal as we call it. So we have this equation, EMF is equals to V lost plus V external. And another way that we can write this is EMF is equals to I times by small r plus I times by big R. So that means that V external is equals to big I times by big R. If we then factor out the I, we can see that EMF is equals to I bracket small r plus big R. So now we need to know what exactly the voltmeter reads. When the switch is closed, like the diagram on the left, this reads V external, whereas where the switch is open, like on the diagram on the right, this reads EMF. So the lost volts cannot be measured directly by a voltmeter, and this is why we use the equation EMF is equals to V lost plus V external. So let's take a look at this experiment and how it relates to the graph. So in the top left-hand corner, we have EMF is equals to I times by small r plus I times by big R. And we know we can write this in a bit of a different way. We can say EMF is equals to I times by small r plus I times by big R, which is also equals to V external. So now, if we look at our graph, we can see that on the y-axis we have V external and on the x-axis we have I. So we're used to seeing graphs in the format of y is equals to mx plus c. So let's get this equation looking a bit more like that. So if we take the V external, or the I times by big R, to the other side, we have V external is equals to negative R times by big I. And you'll see why I wrote it like this in a little bit, plus the EMF. So if we relate this to the equation of a straight line, V external is on the y-axis, so this is like our y variable. The negative R is then related to our gradient, and we can see it's a negative slope. And because I is on the x-axis, this is like our x variable. And the EMF is like our C value. So this means that over here, this is equals to our EMF if we read it off of the graph. So now let's see what happens if a resistor burns out. What is going to happen to the lost volts? Well, if the resistor burns out, let's say this one, this is going to mean that the total resistance in this parallel circuit over here is going to increase, which means that the total resistance in the whole circuit is also going to increase. EMF has got to stay constant. So let's write that here. EMF is constant. So now if the total resistance of the circuit, is increasing, this means that current is going to decrease. This also means that the current through the cell is going to decrease as well. Now, we know that the internal resistance, denoted by small r, stays constant. So if internal resistance is decreasing, we're going to look at our equation V lost is equals to I times by small r. So if small r is staying constant and I is decreasing, we'll see how the V lost is also going to decrease. So that is what's going to happen if a resistor burns out. So here's an example that you're going to try by yourself. It says in the following circuit, the cell has a significant internal resistance. The resistance of the connecting wires can be ignored, and they've given you an EMF of 26 volts. So pause the video and give this a try. I hope that went well. Now let's take a look at this question together. So it says we've got to find the potential difference across the parallel connection. Well, let's start off by looking at the second branch because we can work out the potential difference across the second branch. So we know that V is equals to IR, and if we're dealing with the second branch, we know that the current through this is 0.5 amps and the resistance is 6 ohms. So if we work this out, this comes to 3 volts. And this is the potential difference across that second branch, but because this is a parallel connection, we know that the voltage over the second branch is going to be equals to the voltage over the first branch. So we can then, so then we've actually worked out our answer. That is question A. Then question B is asking us to find the total current through the cell. So from the question that we've just done, we know that the voltage through the first branch is 3 volts. So we know that current is equals to V over R. And now we're dealing with the first branch. So the voltage through this we've said is 3 volts and the resistance is 2 ohms. And if we work that out, that comes to 1.5 amps. So that is the current that's flowing through that top branch, and we've been given the current for the second branch, which is 0.5 amps. So we can find the total current, I total, which is just the sum of these two, so 1.5 amps plus the 0.5 amps, which gives us a total of 2 amps. And this is then the total current through the cell. So if we move on to question C, let's clear the board. Question C asks us to find the reading on the voltmeter. So this voltmeter, which is across the cell, is then a measure of our V external. So we know that V is equals to I R, right? So what we're going to have to do is find the voltage across the 10 ohm resistor and the voltage over the parallel connection we already know from the previous questions. So if we're working out the voltage over the 10 ohm resistor, V is equals to IR. We know that the current we've worked out, the total current is 2 amps from the previous question. The resistance is 10 ohms, which means the voltage is going to be 20 volts. And now to work out the V external, we're going to plus this 20 volts, which is the voltage over the 10 ohm resistor, plus the voltage over the parallel connection, which was 3 volts. That gives us a total of 23 volts over the cell. Right, so let's move on to question D. Question D asks us to find the lost volts. So we can't measure the lost volts with any voltmeter, and we need to use an equation. This is going to be our equation EMF is equals to the V lost plus the V external. And you'll see that we actually have 2 of these elements out of the 3, and we can solve for the V lost. So let's isolate V lost, and that gives us EMF minus V external. In our question, you can see they've given us the EMF as 26 volts. And we've just worked out our V external in the previous question as 23 volts. Sorry, that should be 26. So 26 minus 3 gives us 3 volts. And this is essentially our V lost, which concludes this question. Thanks for joining me today. I hope this helped, and catch you next time.